Delving deep into scikit-learn's RFECV recursive feature elimination with cross-validation. RFECV recursive feature elimination with cross-validation is a powerful feature selection technique within the scikit-learn library. It combines the recursive feature elimination RFE approach with cross-validation to identify the optimal number of features for a given machine learning model. Let's break down its workings, advantages, and considerations. 1. The core mechanism. Recursive feature elimination RFE. This method works by iteratively removing features that contribute least to the model's performance, eventually reaching an optimal subset of features. It relies on a specific model like a decision tree or a support vector machine to evaluate the importance of each feature. Cross-validation CV to avoid overfitting and ensure a robust feature selection. RFECV employs cross-validation. This involves splitting the data into multiple folds, training the model on a subset of the data, and evaluating its performance on the remaining fold. This process repeats for different folds, providing a more reliable estimate of the model's performance on unseen data. 2. How RFECV functions in practice. 1. Initialization. You provide your data features and target variable, the machine learning model you want to use for feature selection, and the number of features to be selected or a range of feature counts. 2. Iteration. RFECV starts with all features and uses the model to rank them based on their importance using techniques like feature importance scores from decision trees or coefficient magnitudes in linear models. The least important feature is eliminated. The process repeats, training the model with the reduced feature set, ranking features again, and eliminating the least important one. 3. Cross-validation at each step. At each iteration, RFECV performs cross-validation to evaluate the model's performance with the current feature set. This ensures that the feature selection is not solely based on the performance on the entire dataset but on a more robust estimate obtained through cross-validation. 4. Optimization. RFECV continues this process until a specified criterion is met. Typically the maximum number of features you set or when the model performance starts to degrade significantly. 5. Optimal feature set. Once the process finishes, RFECV identifies the number of features that yielded the best performance across the cross-validation folds. The corresponding feature set is deemed the optimal one. 3. Advantages of using RFECV. Automated feature selection. RFECV automates the process of finding the optimal number of features, saving you from manually experimenting with different feature subsets. Robustness. Cross-validation mitigates the risk of overfitting, making the selected feature set more likely to generalize well to unseen data. Improved model performance by selecting only relevant features. RFECV can lead to a more accurate and efficient model, potentially reducing training time and complexity. Insight into feature importance. The feature ranking obtained during the process provides insights into which features are most important for the model's prediction. 4. Considerations and trade-offs. Computational cost. RFECV can be computationally expensive, especially with large datasets and models. The number of iterations involved in the recursive process can lead to significant processing time. Model dependence. The feature selection outcome is dependent on the chosen machine learning model. Different models may prioritize features differently, leading to variations in the selected feature set. Hyperparameter tuning. You may need to tune hyperparameters of the model like the number of trees in a random forest to ensure optimal performance during feature elimination. Data requirements. RFECV works best with datasets that have a reasonable number of features and instances. For extremely high-dimensional datasets, other feature selection techniques might be more efficient. 5. Practical example with code. Python. From sklearn, features election import RFECV. From sklearn, linear model import logistic regression. From sklearn, datasets import load iris. From sklearn, model selection import train test split. Load iris dataset. Iris load iris. X iris. Data. Y iris. Target. Split into training and testing sets. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. Create RFECV object with a logistic regression model. RFECV estimator logistic regression. CV5. Scoring accuracy. Fit RFECV to the training data. RFECV. Fit X train. Y train. Print optimal number of features. Print optimal number of features. RFECV. N features. Get selected features. Selected features X train. RFECV. Support. Train model using selected features. Model logistic regression. Model. Fit selected features. Y train. Evaluate model on testing set. Accuracy model. Scores test. RFECV. Support. Y test. Print test accuracy. Accuracy. In summary, RFECV provides a comprehensive approach for automated feature selection by combining recursive feature elimination with cross-validation. It offers a robust method for identifying the most relevant features for a given model, potentially improving model performance and providing valuable insights into feature importance. However, it's crucial to be aware of its computational cost and model dependence, and carefully consider its suitability for your specific dataset and problem.